Hello everyone, my name is Ji Xuanzhi. I come from George Mason University. Today I will present our work, Learning to Herd Agents Amongst Obstacles from Optimized Surrogate. Let me start by introducing the idea of the shepherding. Shepherding is defined as one or more shepherd robots try to guide a team of agents from a start position to a goal position. It has many applications such as animal herding and crowd control. There are two major types of shepherding methods, rule-based method and learning-based method. Rule-based method define a set of rules for the system status. They can handle complex environment, but fragile due to the difficulty in defining comprehensive rules. Learning-based method use machine learning techniques which do not need the knowledge about the model. However, this learned model can only handle simple environments or 2 to 4 shape in obstacle field environments. To overcome those limitations, we propose a new learning framework. Here is an overview. Given an environment field with obstacles and a group of agents, our approach generates an optimal potential field, which used as a surrogate to train an optimal herding policy by deep reinforcement learning. First, we need to construct an optimized global potential field. With this potential field, group members can follow into a goal state by following the gradient without considering the controllers. The potential field includes attractive and repulsive potentials. They are parameterized by distance to the goal, distance to the closest obstacle, and the scaling filter. To find the optimal parameters, we use travel time and group cohesion as objectives to optimize the parameters. Secondly, we use deep Q-learning to train the model guided by the optimized surrogate. Namely, during the actual control, the planner positions the shepherd near the group to produce a force, approximating the force resulting from the potential field. This learning framework works as follows. The input is a sequence of local frames. The output is one of the discrete actions in 8 directions. The reward includes force projection reward, violation reward, and task completing reward. Let's see the input. The figure on the left shows the global view of the workspace. Then we choose the shepherd as the center, create an observation space. The figure on the right is a local view, which is our input. In the local view, we represent the contour of the group as a pixel blob in the intensity map with a bounding circle. We also use different pixel values for different objects. In addition, we choose the average gradient direction of the flock to represent the potential field function. We use a void group behavior model here. Separation force maintain a distance from others, alignment force align with others by velocity, and cohesion force cohere here with others by position. And we add fear force to maintain a distance between shape and shepherd. The behavior of the shape is a weighted linear combination of those forces, and by changing the weights, we can simulate different group behaviors. To train the shepherding controller, we add random noise to the behavioral and environmental models. For instance, we can change the global behavior coefficients randomly. We also consider 2 types of obstacles in the environment, predefined obstacles and perturbed obstacles. We first consider the environments with predefined obstacles. We set 1 start position and multiple goal positions. Figures show 2 different fixed environments, and we randomly change the global behavior parameters from a Gaussian distribution. Next, we treat the controller in environment with randomly perturbed obstacles. We create 3-layer obstacle environments and perturb the position and angle of each fence using a Gaussian noise. In addition, the shorter fence may appear or disappear randomly, thus change the difficulty here. Like the scenario with fixed obstacles, global behavior coefficients are randomized. To evaluate the proposed method, we highlight the effectiveness and the robustness of the trade model over the 2 rule-based method. The shifter with simple rule moves straight behind the group. The shepherd with complex rule method uses a stop-turn policy. We compare the robustness using two metrics, success rate and pass quality. Pass quality includes completion time, pass length, maximum radius, and energy cost. This figure shows the success rate of three-layer perturbed obstacles with different gaps. Consequently, the success rate of the learned model remains at least 10% higher than the rule-based method for 7 or 8 shapes. We also compare the method to the previous method, deep Q learning with route map. This figure shows the success rate for 3 shapes in different levels of fear force in the three-layer environments. It shows the proposed method preserves a higher success rate than the other 3 methods. We also conduct environments for pass quality. Figure on the left shows a maximum radius of success cases under different levels of separation and cohesion. The trained model maintains a smaller maximum radius on average than the other 2 route-based methods. Figures on the right shows energy cost in unit time. The proposed method has less energy cost than the complex rule method, but more energy cost than the simple rule method. In addition, the method maintains a stable energy cost in unit time with smallest standard deviation. In this work, we use optimize the potential field as the row gate to speed up the training of the shaping model in obstacle field environments. We also propose a new representation with pixel blobs. The trained model provides better control quality in comparison to the rule-based method and the previous learning method. There are some limitations in this work. When the number is larger than 10, the performance decreases. The video shows 3 methods for shepherding in 3 different environments: the lattice environment and the pass, the Pekingo environment and the pass, and the 3-layer environment with a pass. Thank you very much.